Hello and welcome to another worked example in section 2.2 forces. This is worked example 2.25 on page 73. In the figure below, a block of mass capital M is connected to a smaller block of mass little m through a string that goes over a pulley. Ignoring friction, find the acceleration of each mass and the tension in the string. This is such a common problem in grade 11 physics. A lot of times there is friction, which is really only one extra step in the problem. Sometimes the values are actually given as well. In this case, the values are not given. Now in the book, they pre-draw you the free body diagrams. I really encourage you not to look at that. Try to figure it out for yourself. And I'm going to show you step by step how to draw it, how to set up the problem, and how to solve it. Okay, so I have two objects here. So I have mass capital M over here, and I have mass little m over here. Each of those is experiencing some kind of force. Now, usually this system is traveling like this. For this kind of a problem where you have two blocks connected by a single string and moving over a pulley, there is a certain way to solve this kind of problem. And in the homework, you're actually going to see a similar type of problem, except the blocks are going to be on an incline, and you're going to do the same thing, okay? So for each block, first of all, you want to set up a free body diagram. I mentioned in earlier videos, in the lesson videos, that it is so important to use Newton's second law. Newton's second law appears in almost every single problem, if not every problem that you're going to do. Either F net is going to equal ma, or F net will equal 0 if the forces are in equilibrium. But before you get to writing Newton's second law and crunching out all those formulas and numbers, you have to draw a free body diagram. The free body diagram is what tells you what goes in the Newton's second law expression, specifically what to replace F net with. All right, so let's start with mass little m. I think that one's going to be easier. Okay, so it has mass by definition, so there's going to be a weight associated with it. So we're going to call that W. Now, personally, I don't like calling it M and M. I'm going to call this 1 and 2. So this is going to be weight 2, and there's one more force acting on it. There's no normal force because it's not touching a surface, but there is tension, right? It's connected to a rope that's going over a pulley. So there's a tension force going up, and I'm going to call that T. I'm not going to call it T2, and I'll explain that in a moment. For block M, now block M also has weight, and it's significantly larger, so if you want, you can make the arrow a bit longer. So that's W1. It's sitting on a tabletop surface, so there's a reaction force, there's a normal force. Okay, so in fact, I don't actually have to draw the arrow so long, but this is, that's okay, I'll keep it for now. So that's N1, and there is a tension force going to the right. So there's T. The reason I didn't call these T1 and T2 is because it's the same rope. If you remember in one of the earlier lesson videos, there was a scenario where you had a ceiling and you had a knot, and then you had another rope and then another mass hanging like this. And in this problem, we had to find the tensions in each of the strings, and we called them T1, T2, and T3. The reason why all of the tensions were different in this problem is because they were all different ropes. This is the same rope, even though it changes direction. When you have the same rope, the tension throughout the entire rope is the same. So we don't have this scenario this time. That's why we just call it T, because whatever tension I have here, it's the same tension here. They're just going in different directions. Speaking of different directions, if you watched my video on the other worked example, 2.21 on page 68 involving the elevators, I would have explained that whatever you choose as your positive direction, that should be the direction of your acceleration, right? So if this system is in fact moving down and, well, right and down, that means little m is moving downwards and capital M is moving to the right. And those are the directions that they would be accelerating in as well when they start moving. So what that means is that for this free body diagram on the right, I'm going to let the positive direction be down. And for the free body diagram on the left, I'm going to let the positive direction be to the right. So very important for this kind of a question, you actually have to define different positive directions. Now, for the little mass, I only have vertical forces, so I can only, it's sufficient for me to define one direction to be positive. But for capital M, well, I have two perpendicular directions, right? I have y and x. So I'm going to call upward positive y and right positive x. Okay, for this one, you don't even have to label it. All right. So for mass 1. So we're going to do sum of the forces, and we're going to look at some of the forces in the x direction, because after all, this block is not accelerating up and down as it moves down toward the pulley. It's just sliding constantly. So in the y direction, the sum of our forces is 0. In the x, sum of the forces is equal to ma times x. We are not going to set acceleration to 0 because that's what the question's asking us to find. Find the acceleration of each mass and the tension. So in the x direction, I only have tension acting on this. What I said earlier is that since this is a really common question in physics, this usually comes up, this type of problem, I should say, a lot of times there is friction. If there was friction here, that means there's resistance between these two surfaces. You would just draw an extra arrow coming out towards the left here and call it FFS if it's static, or FFD if it's dynamic, if the system is moving, which it is here. All right, in that case, then the sum of the forces in the x would be T minus FFD, okay? But in this case, we just have tension. So tension is equal to ma times x. And actually, you know what? Since we're dealing with a capital M, I should call this capital M, because lowercase m is being reserved for the tiny mass. So capital MAX, capital MAX. Okay, so it seems like to find the tension, I need the acceleration, and to find the acceleration, I need the tension. Okay, fantastic. So let's go to scenario 2 or system 2. So in this case, we're looking at the sum of the forces. I guess we can just call this the y direction. Let's call that positive y. And that's equal to MAY. And let me just say one thing here. At this point, it's kind of ridiculous to call these AX and AY. Usually we do, but in this type of a problem, you really don't need to state this. And the reason why is since it's the same rope, I mean, if M is dropping really fast, capital M is moving to the right at that same really fast speed with the same acceleration, because they're attached with a string, not an elastic band. This is not something that can stretch or compress, but definitely not something that can stretch. So however fast M moves, capital M is going to move exactly the same. So the magnitudes of the accelerations are the same. I don't need to specify that they're X or they're Y. Okay. Really, the only reason I put Y here or X here is so that I know for myself I'm dealing with certain directions. Okay, so in the y direction, I've defined down to be positive, so that's W2 minus T is equal to MA. And this is the correct M since we're dealing with the lowercase m mass here. Weight is mg. We'll keep that lowercase, so mg minus T is equal to MA. Okay, so why don't we isolate for T here and then set the two T's equal to each other. So T is equal to mg minus MA. Now let me think here. Probably something you don't want to do. It's really tempting at this point to factor out the M. Don't do that because then your A is going to be mixed up in an expression involving G. And you don't want that. You want to eventually isolate for A. And if you factor out a different letter, you're not going to be able to isolate A. Okay, so now we have these two formulas. Whoops. We've got these two formulas. So we are going to set them equal to each other. So set equal. So here we go. So we have T is equal to T. So then this T is capital M times A, and the other T is little m times G minus little m times A. All right, we're trying to isolate for A. So get all the A's on one side. So we'll have capital MA plus little ma is equal to little mg. Now you can factor A out. I just didn't want you factoring out mass over here. So you get capital M plus little m is equal to little mg. Now you're trying to get A by itself, so divide by what A is currently being multiplied by. So A is equal to mg over capital M plus little m. And now our answer is in terms of the masses, and well, g is a constant. That's fine. You can leave that as is. So there is the acceleration, and that is the acceleration of each block. Remember, like I said, because they're connected with a single rope. So there we have that. Now to find the tension, you just plug that into either one of these formulas. I'm going to plug it into this one because it's simpler. So T is equal to MA. So T is equal to M times mg over m plus little m. And this is the tension for both of them. Whether you were to plug in this here or this here, you will get the same answer, depending on how you simplify it, but it is the same. So these are the acceleration and tensions for each of the objects. So that is it for this video. I hope that made sense. If you have any questions, be sure to let me know. Otherwise, I will end the video here.